I wanted to thank Krishna and Nita for their excellent presentation, but they, I guess, left way too early. So just like we saw that predictive analytics can be applied in legal system, we are going to talk about how it is applied in healthcare, which is quite different from the nature of the industry we're dealing with, but from the technical standpoint, there are a lot of similarities. So before I commence my talk, I wanted to, is this in the presentation mode? Is this in the presentation mode? Okay. Okay, that's fine. So before I commence my presentation, I wanted to tell you a story about Betsy. So Betsy is a 58-year-old woman. She has 2 kids, and she has 4 grandchildren. She loves spending time with her grandchildren. She hangs out with them over the weekend. She takes them out. She's very active. She also leads a very healthy lifestyle. She eats healthy. Not to mention that she visits her doctor every year for her annual checkup. Betsy feels very, very well for her age. She has mild issues with her health like high blood pressure, potentially sometimes high sugar levels, but overall she feels really well. In the last 2 months, Betsy started feeling drowsy, tired. She can't spend as much time outside as she used to. She can't even spend a lot of time with her grandkids anymore because she can't focus as long as she used to focus before. She doesn't think much of it, it's all the part of aging process, but she does go to her primary care doctor to get a blood test done as part of her annual. A week later, a doctor realized that there is something wrong with her blood count. He orders a little bit more tests, and in 2 weeks of time, a morbid diagnosis has been established. Betsy has a rare type of blood cancer. Everyone is in shock. How a healthy person like Betsy could get a morbid diagnosis like that? Not only now she has to fight the cancer, she has to stay on therapy for her entire life. Blood cancer is not resectable. You can't remove a part of your own organ and hope for the better. You have to be on treatment for the rest of your life. Betsy, being a fighter, schedules her appointment 1 week after the diagnosis is done. She visits an oncologist. An oncologist confirms the diagnosis and starts the treatment right away. He's very aggressive. He also orders a biomarker that's used to monitor her cancer. And Betsy, taking medication diligently, being very determined to fight the cancer, she gets better. Her biomarker goes down to undetectable level of remission. And Betsy and her family are cheering because she is getting into remission. She is now not cured, but under control, or took the control over her disease. Now she feels, although she's getting better, her side effects are really affecting her quality of life. Now imagine, you are a healthy person. You think you have a disease which you fought, but you don't feel great. You have rashes, you have migraines, you are even more tired than you used to before. She decides to seek a second opinion. She goes to a second oncologist who tests her biomarker and sees that it's way above the remission level. The oncologist doesn't think much of it because Betsy only started on her treatment a few months ago, so he thinks she will eventually get into her remission. Betsy doesn't really think much of it, goes to her previous doctor, first doctor, 3 months later, because she's now in remission, she thought she was in remission. And the doctor is furious. She is now officially in clinical relapse. Clinical relapse means you have to fight your cancer all over again. Betsy's put on the second treatment. So who is the one to blame here? Is it the first doctor? No. He followed all of the guidelines that he was supposed to follow. Is it the second oncologist? Well, hardly. He had no context in her Betsy's history of disease. Is it Betsy? Well, as intelligent as she is and as hardworking as she is, she can't remember every single test result that she had. The problem is that data for Betsy is not connected. The issue of the connectivity is the reason why Betsy has a clinical relapse. Now, this is the topic of my presentation today. I'm going to talk about how Medivo developed a technology to solve this problem, to bridge the gap between laboratories that tested Betsy and understood whether she was in remission and went out of the remission into the clinical relapse. So, ladies and gentlemen, let me tell you about, I will go through the summary, I will tell you what we did and the technology that we built. I will also give you some background because it's a US system. It has intricacies that may or may not appear in the Indian market, but I'm sure there is a lot. As we can make labs talk to each other and get connected, we can come up with a data set that no one else in the US has that will enable physicians and organizations as like others or like us. So Medivo aims to unlock the power of data, of diagnostics to improve health. The data currently that we work with is not harmonized and not standardized, which is what I was conveying right before the presentation came back. As long as we can increase the analytical utility of the data just by harmonizing it, I'm not saying doing anything else, just by harmonizing, making it all standard, we can increase the analytical utility of the data. Finally, Medivo applied machine learning algorithms to harmonize this data. You can hire hundreds and hundreds of physicians to tell you which tests stand for what, but at the end of the day, if you can come up with something very scalable, if you can build an algorithm, you can, in fact, standardize the data and look at the patient's longitudinally. A little bit of background. So remember Betsy, she went to 2 doctors, and 2 doctors used 3 labs. Now, usually it's a lot more than that, but let's imagine it was three labs. 3 labs label their tests very differently, but they all mean the same thing. In her case, she used the biomarker for cancer. Here it's hemoglobin A1C, which every one of us is supposed to get every year. Call your doctor if you haven't. But the hemoglobin A1C is labeled by each lab differently. It's even coded differently. So how am I, as an analyst, can determine which test is what when I look at data across the sources? Well, we developed an algorithm that intakes all this data and runs it through the machine learning with a module that has a machine learning algorithm in it. And it standardizes the data to the point where we can say that hemoglobin A1C across all 3 different sources is the same, and we even can come up with an identifier. Let me give you some background about the US system. So this question that I'm posing right now, it has been in existence for a long time. We haven't invented it. And the way American system was trying to tackle this problem was by introducing something that's called LOINC. LOINC is basically a uniform codification system for all the tests in the US. And America forced their labs to, in addition to their internal code, to introduce this external code, a LOINC code, which then laboratories could use to track tests for patients across different sources. Now, we all know that the data in reality is not always there when we expect that to be. And so a lot of LOINC codes were actually missing from the data. And that was the reason why Medivo decided to solve the problem and actually introduce an algorithm that was very reliable and people could actually count on when they go into the data, when they pull the patient journey, when they track patients longitudinally. In our data set, which has 4.6 billion records, 100 million records has missing LOINC codes. Now, when you think about the 100 million out of 4.6 billion, what a big deal. Well, that translates into 14.8 million patients. 14.8 million patients like Betsy have a high risk of delayed diagnosis, a complication in their disease, and clinical relapse, like we saw in our first example. Solution? Medivo developed a machine learning algorithm that took the data from its upstream. We pulled all the raw data, basically. And we developed a model, a statistical model, that could then take all the records with missing loin codes and predict the loin codes based on a large longitudinal, basically a longitudinal data that we used as a training set. And that data had, in fact, the loin codes. The point that Krishna mentioned in the previous conversation, he said that you always need to make sure that you have a good representation of each outcome. So we had a big data set to begin with, and that helped us basically with that problem. Now, when we applied the algorithm and we put the real data through that algorithm, we get the harmonized Medivo lab data set, which then can be used downstream by all the internal and external customers. A little bit about the approach. This approach is very typical for agile organizations. I'm sure most of you know that this approach. Not that many healthcare startups in the US apply this approach in their organizations. Data science is usually looked upon as a research group, and they are partially separated from the overall agile teams. That's not the case at our company. Our data scientists work along with engineers and product teams to make sure that there is a continuity, and we adopt the same agile approach here. So we extract the data, we transform it, we train the models, we validate the models, and if the model is performant and is accurate, we deploy it to the production data. If it's not, it goes through the same process all over again. Now, when the models are deployed on the production data, we get a harmonized data set that then can be used by our clients, by our partners, even by internal employees who have to do some data mining and exploration. Technology, so I'm going to talk about the tech stack. So the problem we were trying to solve was a multi-class classification problem. Now, in the previous presentation, we saw that there were tens, I think, of different classes that the team was trying to tackle. Now, we had 700 plus classes. No traditional technology that's out there is capable of handling this many classes in the time that would be feasible for an organization. So we had to go for big data technologies like Spark, and we actually adopted Spark across the organization. So if you guys have a familiarity with Spark, I'm sure you would appreciate that. Databricks, we use it for the interface. They actually make it really easy. It's a notebook type coding style, and you can actually see the output every line code that you type. As far as the machine learning algorithm, we looked into the TensorFlow and H2O. We ended up using H2O along with Spark, and the overall combination was S2O that we ended up using, which is commonly referred by the data science community as a sparkling water. Let me tell you a little bit about the models. We tried 3 different models in our case. We tried random forest, logistic regression, and naive Bayes. Naive Bayes ended up to be the most performant and the most accurate model. And that was the model that we've incorporated into our version 1.0. I'm not going to bore you with all the data transformation. There was a lot of data transformation happening, and previous presenters actually went through a lot of details into the data transformation steps. But I do want to mention one data transformation step that made a huge difference in the way we were performing or running the models. So if you think of the way labs represent their tests, they are all either codified or tests have their names or they come from a specific lab. And there's so much variation across different labs, but you want to hold on to something that's common across sources. So what is it that's common across sources? Well, that's usually the test name. So hemoglobin A1C is usually referred by the same name or a synonym or a combination of the same name by different labs. Here there is an example of cholesterol. So you have LDL cholesterol, cholesterol triglycerides, cholesterol total. They all mean the same thing. They're spelled very differently. They may even be misspelled. But what we did, we used the method of TFID, of textual transformation, which is a tokenization of the words in the test result name field. And what it does, it basically groups the names and the synonyms into the bigger buckets. And it makes the groups, it creates the groups that are very similar to each other, so that they can be used as independent variables in the model. This is the output of the 10 conditions that we performed. We actually ran the model on 20 plus conditions, but this is a snapshot of 10 of them. The model accuracy for all of them was over 98%, which is actually a really, really good result. And if you think about it, the conditions that we used for predictions were mostly, you can see here, there were mostly cancers, viruses, the infectious diseases, and primary care conditions. These conditions affect more than 60% of the US population. If you can reconstruct the full history of the patient for more than 60% of the US population, think about how many patients can be saved, how many lives can be saved from deterioration of the condition, from complications, and from relapse. As I mentioned in my presentation, we used various big data technologies. We looked at the most cutting-edge technologies that are out there, not because we wanted to play around, although we did want to play around with new technologies, but not really because of that, but mostly because we didn't have any other choice. We had 4.6 billion records, and we had millions and millions of patients. We had to deal with it with technologies that go beyond traditional. And we were also able to come up with a statistical model that was able, with a high level of accuracy, predict the low encodes. That translated into the classification of 100 million records, which was basically 14.5 million lives saved as a result of deployment of a fairly simple algorithm. Not that it was simple from the technical standpoint, but from the overall healthcare standpoint, the algorithm made a big difference, and it was just one problem that we solved. This is just an example of Medivo does from its data science standpoint. These are some other examples that we utilize to tap into each stage of the patient journey and make the data better, more performant, more accurate, so that this data can help us look into each stage of the patient, reconstruct the picture, and then make meaningful insight based on that. We perform analysis in data text mining in NLP because we deal with a lot of unstructured data. We also conduct things like multivariate statistics and network and cluster analysis. Unsupervised learning is a big thing for us because we segment physicians and we try to understand their behavior. And finally, we perform some of the graph analysis, neural networks, to understand the referral patterns of the physicians. How one physician refers the other, for Betsy in this case, to make the diagnosis. We follow that so that we can identify more patients in need of care. Medivo is an advanced analytics company that utilizes the power of diagnostics data, healthcare data, to provide meaningful insights and make impact on our clients and partners. We have 300,000 physicians in our network with 150 million patients. 150 million patients is half of the US population. Imagine what technology we need to have to handle this. And imagine how many people could be saved with tackling problems like I mentioned with Betsy, so that the lives of the American people who visit their doctors could be improved. Now think how this could be applied to the Indian system. I'm sure there's a lot of discontinuity amongst different organizations in healthcare and in other industries, in legal, for example, like we saw in the previous presentation, that could be solved by an algorithm like this. I want to finish this presentation by saying that we saw a lot of real cases like Betsy's. I didn't make up the story. It's actually very fascinating when you tell a sales rep to go see this doctor because this doctor may have a patient on the verge of clinical relapse who really needs your help. I cannot express how much gratitude you get when you identify these patients, when you identify the care that's been given them, and then you can actually reverse a disastrous consequence of the patient who could have been basically diagnosed again and had to fight their condition again. One thing I also want to mention is we're hiring. We have a team here in Bangalore, which is actually as big as our US office, or almost as big. So if any of you here or any people who you know are interested in joining the team and work on stuff that really matters, and work on cutting-edge technologies, work with really cool languages that are out there and evolving, please talk to me after this presentation, or we have a whole crew of medivators here who could answer your questions and tell you about all the cool stuff that we do. Thank you.